Chapter 3.3, Truth Tables for the Conditional and Biconditional. So in this chapter, we're going to hit on the last two of our truth table operations. So we've seen the truth tables for negation, conjunction, and disjunction right here, and now we're going to see conditional and biconditional. So the conditional is probably the most unique out of all of them. It has a property that the rest of them don't have, so this is one you're really going to want to pay attention to. So, the conditional, which is written as P arrow Q, and read as if P then Q, or P implies Q, is false only when P is true and Q is false. So notice that in all of our previous truth tables, there was a sort of symmetry to it, where if we look at the conjunction, our and statements, if one is true and one is false, they're both false, right? Regardless of which one it is. And for the disjunction, if one is true and one is false, we get true, regardless of which one it is. Right? So there's a symmetry to it where it didn't really matter what order this was written in. But for the conditional, it very much matters what order we write this in. Right? Because if I say I'm going to the store and the bank, it's the same thing as saying I'm going to the bank and the store. It doesn't matter which order I say that in, right? It means the same thing. But if I say an if-then statement, well, it does matter because one is the cause and one is the effect, right? So the order I say them in matters, which is why we get this truth table that doesn't have that same symmetry. The odd one out, which, just like the other ones, had odd ones out, right? Our odd one out here was true, true, and true, and our odd one out here is false or false, gets us false. But everything else is true. So for the conditional, the odd one out is if true, then false. So let's see an example of why that is, though, because that's going to feel a little bit weird. Why would that one be the odd one out? My favorite example of this is, let's say you're a little kid, and your parents tell you if you eat your vegetables, then you'll get ice cream. And the question then becomes, in what situation would they be lying? So let's go through each of the four. So case one, we get, you do in fact eat your vegetables. So eating your vegetables is true, and they give you ice cream. So getting ice cream is true. So that's if true, then true. Did they lie to you? You ate the vegetables, they gave you ice cream. No, obviously they didn't lie to you. Exactly what you assumed would happen, happened. So that one is true. They didn't lie to you. Now I'm actually going to skip case 2 and I'll come back to it. Case 3. This one is an interesting one because essentially it's saying you don't eat your vegetables. You're a bad little kid. You choose not to eat your vegetables, but your parents give you ice cream anyway. Now, did they lie to you? And here is where a lot of people make the mistake of thinking that, yeah, they did. But in fact, no, they didn't. They never said anything about what happened if you didn't eat your vegetables. They just said, if you do, you'll get ice cream, but maybe. For example, they were planning on driving to the ice cream shop anyway, and they didn't change their plans just based on you eating the vegetables. That was an incentive. They implied it, but it's not stated. So they never lied to you. In fact, your parents were just very nice. You were going to get ice cream either way, is basically what happened. But they made it seem like, well, if you eat those vegetables, you'll get ice cream, even though you were going to get it anyway. Maybe a better example of this would be, think about, like, if they say, if you eat your ice cream, if you eat your vegetables, we'll go to Disney World. Do you think they're really going to change their trip plans based on you eating your vegetables? No, but they can make you think that that's possible, right? So, no, they didn't lie. They manipulated you a little bit, and it didn't work because you didn't eat the vegetables anyway, but that's it. So, case 4 is where you don't eat your vegetables and then they don't give you ice cream. So that's what you would have expected to happen, right? So clearly, there's no lie there either, because once again, they never say anything about what's going to happen if you don't eat them. They just say if you do eat them, this will happen. But if you don't, who knows? So whether they give you the ice cream or not doesn't matter, because they never said anything about what happens if you don't eat ice cream. I mean, if you don't eat the vegetables. Now, if we go back to case 2, this is the one that's our odd one out. Here is where you eat the vegetables. You're a good little kid. You eat your vegetables. You eat them right up, and you expect what they told you to be true. You expect that you would get ice cream. But in fact, Q here is false, which means that they don't give you ice cream. So you ate your vegetables. You were the good kid, but then they don't give you ice cream. Now they actually did lie to you, because they told you what would happen if you ate those vegetables, but it didn't happen. So your parents are lying. That's why that one is a false statement. The other 3 are true because, again, first one, that one's pretty obvious. But case 3 and 4, it's just that even if you think what is called the converse, which we'll talk about a little bit later, but even if you think the opposite should be the way it works, even if you think if you don't eat your vegetables then you won't get ice cream, that's never stated. So it doesn't matter what happens if you don't eat the vegetables. They can give you the ice cream or not, doesn't matter. They never said, they never made any promises about what happens if not. They only made a promise about what happens if you eat your vegetables. So they are only lying to you if they don't give you ice cream after you eat those vegetables. So, that is the odd one out. True, then false. So we have to remember that's the one we're looking for, which is a little bit trickier to look for than just the double true for our and statements and the double false for our or statements. But still just one thing that's the odd one out, so just keep in mind this example because it's a good one for remembering how this works. Alright, so let's look at building a more complex truth table. So here we have negation of P implies negation of Q. Remember that we can read the arrow as if then or implies or like a whole bunch of other words, but I'm going to say implies here. So negation of P implies negation of Q. So when we build our truth tables, we start with our first 2 columns. We've got a P and a Q. We write out the true, true, false, false, true, false, true, false, same pattern as always. Then we move on to our other headers. So our other headers, we're going to need direct negations of both P and Q because we have the negation of P and we have the negation of Q. Then, once we have both of those direct negations, we can add in our conditional between them, like so. Because we'll have either side of the conditional already accounted for. Alright, so to do our negations, we know that our negation just takes whatever we have and flips the truth value. So if it was true, it becomes false. If it was false, it becomes true. So we need to pay attention to what our letter is. So this one is a P, so we're going to take everything from P, and the true becomes false, true becomes false, false becomes true, false becomes true, so we get false, false, true, true. And then negation of Q is false, true, false, true. Next, we get to our conditional, and here is where we have to look for the order matters. So we're going to number this. Remember I was numbering in the previous chapter, and I said the order didn't really matter here, but I number it anyway just to kind of get in the hang of things. So here, the order does matter. It matters what is first. So our negation of P is first, and our negation of Q is second. So we need to look for that odd one out, the true false one. So we look for where is it true and where is it false. Where is P negation of P true and negation of Q false. And that happens right here. So that's going to be the odd one out. Now I call it the odd one out because it is one thing in the original table, but do remember that when we're working with the complex tables, sometimes you'll hit more than one thing that looks like that. But we only hit one of them this time. So we get that third row is a false and everything else is true. And that's it. Now our our last operation we're going to look at is the biconditional. So the biconditional statement, P arrow in two directions, Q, means that if P then Q and if Q then P, or otherwise P implies Q and Q implies P. Or symbolically, we could write this as P implies Q and Q implies P, where we put the arrow with the Q, the arrow with the PQ and the arrow with the QP in parentheses with an and between them. We're going to show what the truth table for the biconditional should then look like, because the biconditional is the only one that is defined as a combination of other operations. So here we start once again with our PQ columns, but we also have our P implies Q, our Q implies P, and then the and between them. So first, P implies Q. Remember that we are looking for the odd one out. So the odd one out is our starting true and ending false. This is how I'm going to say it. Start true, end false. Don't get confused over the letters PQ. What you want to think about is that it is true implies false equals false. Like, that's what we're looking for. Starting true and ending false. So where are we starting? We're starting with P and ending with Q here. But on our second one, we'll be starting with Q and ending with P. So here, we start with true, end with false in our second row. So that one is going to be our false statement. Then we switch. 1, 2 becomes 2, 1. So we are starting with when is Q true? So Q is true here and here. When is P false? So that would be the third row is where we start true, end false, if we're starting with Q and ending with P. So we get a false there. Now together, we've got our conjunction, and remember our odd one out is just when both are true. It doesn't matter about order or anything like that, but I'm still just going to get in the hang of numbering these things. So 1, 2, look for where are they both true, but look, this is an example. Like I said, sometimes it's not just one. Here there are actually 2 statements where we get both true, like so. So in fact, the biconditional truth table looks like this. This is the biconditional, which we'll summarize here. The biconditional read as P if and only if Q is true whenever both P and Q have the same truth value. So if they match, if the incoming statements match in truth value, then we get true, otherwise we get false. So there's a really nice symmetry here, right? Matching, matching, we get true. That's what we're looking for. We want things to match. Okay, so now let's make a more complex truth table. Notice here we actually have a P, a Q, and an R in this statement. So negation of P, if and only if the parenthetical negation of Q implies R. So, when we make this truth table, we're going to need 3 beginning columns. Now, how many beginning rows does that leave us with? It actually leaves us with 8 of them. Remember, because it's 2 to the power of how many simple statements we have. So 2 to the power of 3 is 8, so we have 8 rows. Okay, our next headers are going to be the direct negations. So the direct negations we have are negation of P and negation of Q, like so. Then we work from the inside of our parentheses out. Notice that our first parenthesis, we have our negation of Q and we have our R. So we have everything that's made up with, all we need is just the operation between them, like so. Then our last one, we have the left side and the right side. So the left side is the negation of P. The right side is this statement. So we can add in this operation to get the final header. Now when filling out the 3 first columns, there isn't yet again a pattern to it, but the pattern changes a little bit from what we're used to. Because remember, what we're used to is, let's let's just go back real quick. What we're used to is true, true, false, false, true, false, true, false. Now we need to expand that to account for there being 3 first columns. So essentially the pattern is going to be P gets half true, half false, Q gets 2, 2, 2, 2, and R gets 1, 1, 1, 1, 1, 1, 1. Like so. So we get 4 trues, 4 falses. 2 trues, 2 falses, 2 trues, 2 falses. True, false, true, false, true, false, true, false, true, false. So see, it's sort of an expansion of the same pattern that we used previously. Now I'm not going to force you to remember this necessarily, but you'll need to be able to do it for homework, etc. But on exams and such, I would provide you with something like this to start from, just because it makes my life easier as well as yours. Alright, so let's start with our negations. So our negations, we just want to take first negation of P, then negation of Q. So we're taking the P column and just flipping all of our symbols. So it becomes 4 falses and 4 trues. And the negation of Q will become 2 falses, 2 trues, 2 falses, 2 trues, like so. So everything just gets directly opposite of it, right? Then we move on to our first implication. Now remember that the implication, our conditional, is only false if it's true, then false. If true implies false. If true, arrow, false. That's what we're looking for. So if you can remember this simple statement, then you don't necessarily need to have the whole truth table memorized. You just need to know the one thing that stands out. So if true, then false is what we're looking for. So remember, we have to number it when we're working with our conditionals, because the order definitely matters here. It matters that we start true and end false. So our 1 column is negation of Q and our 2 column is R. So we want to look for starting true, so that's here and here, ending false, that's here, 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 here. So where do those actually line up? That's going to be this one and this one, like so. So those are going to be the only ones that end up being false, and everybody else is true. And finally, our biconditional is only true if they match. So we look for, again, 1 and 2, we look for where are they matching. Well, not match, not match, not matching. Oh, these match, right? These match, these match, these match, these don't match. So we get those 4 rows right there are going to be trues and everybody else is false. And that's our final column of the truth table, our final answer. Alright, so now we've seen some complex truth tables with 3 simple statements, etc. We can build them up. We know our basic statements that can help us get there. Now let's look at applying this to some real-world data. So this graph represents the student population by age group for the State College of Florida. Use this graph to determine the truth value of the following compound statements. Okay, so if 44% of the SCF population is younger than 20, or 38% of the SCF population is aged 20 through 29, then 8% of the SCF population is aged 30 through 39. Alright, so let's go through this one by one. We'll get to part B in a moment. So I'm going to break this down. We've got 3 statements in here, 3 simple statements. We've got 44%, 38%, and the 8% statements. That's 3 statements like so. Now, of course, I've color-coded them to make this easier, but let's identify whether or not they are true based on the chart that's given. So 44% of SCF population is younger than 20. So here we have the younger than 20, and yeah, it is 44%. So that one is true. 38% is age 20 through 29. So here's 20 through 29, and that's 41%. So that one is false. And 8% of the population is 30 through 39. That's right here, and yep, that one is in fact true. So we get each of these. All right, so now we want to write the statement symbolically. So here we have if this whole thing is P, this one is Q, and this one is R, and then we want to replace each of the operations here. So we've got an OR right here, so that'll be our V shape. And then we've got an if then, so we've got an arrow, and we just need to think about where does that parenthesis go? Well, we've got comma here, so that means we'll put parentheses around this side to get P or Q implies R. Now we plug in our specific truth values, so that'll be T or F implies T, right? Just using these values right here. So then we break this down, T or F. Well, what do we know about the OR statement? OR statements are only false if both are false. Both aren't false, so we know this one has to be true. So that becomes true implies true. And then what do we know about our conditional statement? It is only false if it starts true and ends false. This starts true and ends true, so our final statement is true. Now let's try the second one, part B. 5% of the SCF population is age 40 through 49, and 5% of the SCF population is age 50 and older, if and only if 41% is age 20 through 29. So that's once again 3 statements. So we will call them P, Q, and R. P is 5% is 40 through 49, Q is 5% is 50 or older, and R is 41% is 20 through 29. So we can go through and we say, okay, 5% is 40 through 49, yep, that one is in fact true. 5% is age 50 or older, well, 50 or older, that's 2%, so that one is false. And 41% is age 20 through 29, that one is true. So we get TFT once again. Now we write out our statement symbolically. So we know this is P, here we have an and, Q, if and only if is our double arrow, and then R. Where does the parenthesis go here? We've got a comma on this side of the if and only if, so we're going to put parentheses around our P and Q to get P and Q if and only if R. So now we replace it with each of our truth values right here to get T and F if and only if T. So we start and we say, what happens to T and F? What do we know about our conjunction, our and statement? Well, and statements are only true if both are true. Both are not true, so in this case it would have to be false. So we get false if and only if true. Then what do we know about our if and only if statements? Well, our if and only if statements are only true if they match, if the values match, and we've got a false, true, they do not match, so our statement in the end is false. So in general, we've seen a lot of different truth table examples, but there are several specific types of arrangements that have special names. So when we finish out a truth table, when we get to the final column, if we run into a certain type of situation, we get these special truth table arrangements, these special names. So the first one is a self-contradiction, which is a compound statement that is always false. So when every truth value in the answer column of the truth table is false, then the statement is a self-contradiction. So if we get to the end of our statement, we're at the end and it's all false, as every single thing in the final column is false, then we have a self-contradiction. Now, an example of a self-contradiction, a very easy one would just be to say, I like waffles and I don't like waffles. I'm obviously contradicting myself. I have said the exact opposite of what I said something, and then I say the exact opposite is also true. That's impossible, right? So this is a self-contradiction. It's not possible for me to be telling the truth because it's kind of a paradox situation. It doesn't make any sense. How could this ever be true? So it has to be a lie. I can't both like waffles and not like waffles. I mean, at least not logically speaking. There are times when I like waffles and times when I don't like waffles, sure, but that's not really what's being implied by this statement. So logically speaking, you cannot have both, and thus, this is a self-contradiction. Next, we have a tautology, which is a compound statement that is always true. So again, when we get to the final answer column of the truth table, we've got our whole table, blah, 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 and the final column is all truths, then it is a tautology. So if I say I like waffles or I don't like waffles, that one is a tautology because one of those two things has to be true. I either like them or I don't. So it's got to be one of those. So no matter what, yeah, I've basically said nothing. That's how tautologies work, is I'm telling the truth, but I'm really not telling you much of anything. Doesn't matter what I said, what is true about it, because I didn't tell you anything. I told you. So tautologies get used actually quite often in very manipulative ways so that people can just avoid giving any information, which is what this is doing. You didn't learn anything about my taste in waffles, right? Either I like them or I don't. What does that mean? Doesn't tell you anything about me. That's the point of a tautology. Then an implication is a conditional statement that is a tautology. So in other words, if we're working with an implication, if we're working with a conditional statement and it happens to end up being a tautology in the end, then it is an implication. So if I like waffles, then I like waffles. Again, I'm not really telling you anything, right? Do I like them or not? Who knows? But if I do, then I do. You didn't really learn anything about me, right? So for an implication, the consequent will be true whenever the antecedent is true. So let's construct a truth table for P if and only if Q and P if and only if negation of Q. And then we're going to say whether or not this is a self-contradiction, a tautology, an implication, anything like that. So here we have, I've already provided us with our header columns. We've got our direct negation of Q, our P if and only if Q in parentheses, our P if and only if negation of Q in parentheses, and then our final and statement that's outside of the parentheses. So we start by negating Q. So I take this column and I change all of the symbols to be true goes to false, false to true, and so on. P if and only if Q, remember that is only true if the values match. So we look at what are the values. This is column 1, column 2. When do they match? They match here, and they match here. So we get true, false, false, true. P if and only if negation of Q, we're getting column 1, column 2 here. When do they match? They match here, and they match here. So that's going to be those two middle statements are true. Finally, our and, it's only true if both are true. So if this is 1 and this is 2, then this is 1 and this is 2, right? Left, right. So when are they both true? Well, never. We never get two truths lining up with each other. So in fact, this is all false. So all false means this is a self-contradiction. And even reading it, it kind of feels like a self-contradiction because essentially we're saying that if P then Q and if Q then P, and if P then not Q, and if not Q then P. So like we're saying P is implying both Q and not Q, and that's not possible, is essentially what's going on. Next, here we have P and Q implies P or Q, P or R. So we have 3 column truth table here, or 3 simple statement column truth table here. And each of our parentheticals, we've got P and Q, P or R, and then our final conditional right here. So we start with P and Q gives us column 1 and 2 to look at. And statements are only true if both are true. So both true, and that's it. Like so. So those are our 2 true rows. Next we have P or R, so that's 1, 2, 1, 2. Or statements are only false if both are false. So we look for where are both are false here, both are false here, and that's it. So everything else will end up being true. So we get our 2 false rows. Now our conditional. Our conditional says it's only false if it starts true and ends false. So we're looking for this to be true and this to be false. That's when we get a false statement. So we go over here and we look at this is 1, this is 2. When do we start true? We're starting true here. When do we end false? I already have it circled. Well, those never line up, which means that it's never going to be false. So it's all true. This is a tautology, but more specifically because the entire thing is an if-then statement, it is an implication. Next, we have P or Q and negation of Q, all in parentheses. Yes, I'm using square brackets here, but that's just sort of to make it more readable. You can think of these as, larger parentheses. And then implies P. So this is another conditional statement, and we are going to work through it. So we start with the negation of Q is our only direct negation. Then we start from our parentheses outward. So P or Q, then larger parentheses, P or Q and negation of Q, then the whole if-then statement. So negation of Q, we take this column and we flip all of the symbols to be false, true, false, true. Next, P or Q is going to be only false if both are false. So here are 2 columns. When are they both false? Right here. So everything else is true and that last row is false. Then we get our and statement between this and this. And statements are only true if both are true. Where are both true? That's going to be this row right here. So we get true in that second row. And then finally our if-then statement. Once again, if this is true, this is false, then we get false, and that's the only time. So we're looking for when does it start true and end false. So starts true here, ends false here and here, but those never line up, and thus it is never false. So it's all true again, and this is yet another implication. Specifically, it is a tautology that is an implication because the outermost, the final column is an if-then statement.